Hi everyone, today we're going to talk about comparing models. And the models we're going to look at comparing are linear, exponential, and quadratic. So let's review the forms that we might see these in. Let's start with a linear model. Some of the equations that we have worked with. Slope-intercept, y is equal to mx plus b. Point slope, y minus y sub 1 is equal to m times the difference x minus x sub 1. And standard form, ax plus by is equal to c. Next model, exponential. The forms that we have seen for exponential, we have y is equal to a times b to the x, and y is equal to a times the sum or difference 1 plus or minus r raised to the t power. And then our third model, the quadratic model, we have standard form, y is equal to ax squared plus bx plus c. We have a revenue form, y is equal to a times x minus p times x minus q. And then we have our vertex form, y is equal to a times the difference x minus h squared plus k. So what we're going to be doing is looking at forms of linear, exponential, quadratic. We're going to look at tables and determine if it's a linear model, exponential model, or quadratic model. And then we're going to look at some real-world scenarios to see if we have a linear, exponential, or quadratic model. So let's start with a table. To be linear, we want the first differences to be constant. First differences to be constant. So remember slope, we did delta y over delta x. So the y value is what we would start with first. So the y column. Difference is to subtract. So if we take 45 minus 47, we get negative 2. 47 minus 49 is negative 2. And 49 minus 51 is negative 2. So we want the first difference to be constant. First difference, your y column. Difference, subtract. Constant, the same value. Exponential model with a table. Exponential with a table. So exponential. We want the multiplication factor to be constant. And we've talked about the multiplication factor before, and we've referred to it as the common ratio. To do this, we want the y column, multiplication factor, what we multiply by, to be a constant value. So 5 times what gives us 15? 3. 15 times what would give us 45? 3. And 45 times what would give us 135? 3. So we want the multiplication factor, what we multiply by, or that common ratio, to be a constant value, 3. This represents exponential. Our third model, quadratic model. Quadratic. We want the second difference to be constant. Second difference, x column. Difference, subtract. 0 minus 1, negative 1. 1 minus 2, negative 1. 2 minus 3, negative 1. So we want the second difference to be constant, the same value, and that represents quadratic. So let's look at two more table examples. So determine if the table or graph, we're just going to look at tables, represents a linear function, an exponential function, or a quadratic function. So linear, exponential, or quadratic. So to be linear, we want the first difference to be constant, the y column. So the y column, 11 minus 4 is 7. 4 minus negative 1 is 5. Negative 1 minus negative 4 is 3. So we don't have a constant. All right, to be exponential, we want the multiplication factor to be constant. So 11 times what would give us 4? Right? 4 times what would give us negative 1? Negative 1 times negative 4. Or negative 1 times what would give us negative 4? Negative 4 times what would give us negative 5? You don't have the same common ratio. As an example, 4 times what would give you negative 1? Negative 1/4. Negative 1 times what would give you negative 4? 4. You do not have a constant ratio. So let's look at quadratic. See if we have a quadratic. So to be a quadratic, we want that second difference to be constant. So second difference, negative 2 minus negative 1, negative 1. 1 minus negative 1 minus 0 is negative 1. 0 minus 1, negative 1. 1 minus 2 is negative 1. So this represents a quadratic model. Second example. Using this table. Linear, first differences are constant. So let's look at first differences, the y. 12 minus 5 is 7. 5 minus negative 2 is 7. So it looks like we're on to something here. So let's continue to check it for linear. Negative 2 minus negative 9, 7. Negative 9 minus negative 16 is 7. So same constant from that first difference. So this is a linear model. So in order to determine, using a table, if you have linear, exponential, or quadratic, linear, your first differences are constant. Exponential, the multiplication factor, or that common ratio, is constant. And to be quadratic, your second differences are constant. All right, let's turn away from tables here just a minute and let's look at real world situations. Let's write the equation based on the scenario given. It says Kristen currently has $45 in his wallet. He earns $2 for every newspaper he sells on his route. This represents a linear function. The constant is $2 for every newspaper, and his starting value, 45. So y is equal to 2x plus 45. Second scenario. Every year Hannah counts her tulips in her garden. The first year she counted 5 tulips in her garden. Recently she has noticed a definite pattern in that the number of tulips triples each year. When you have keywords like triple, double, halves, this indicates exponential. So let's look at y is equal to a times b to the x. Starting value, 5 tulips. And these are tripled each year, 3 to the x. So y is equal to 5 times 3 to the x. Last model, quadratic. Coach Sutton kicks a soccer ball in the air during gym class at a velocity of 60 feet per second. Velocity. So we have In chapter 12, or unit 12, we used your form h is equal to negative 16t squared plus vt plus c. We would plug the velocity in for v. We do not have a starting height, so c would just be represented as 0. Now, some things that will help you with the real world situations. Some key words. If we look at linear first, if you have a problem that requires repeated addition or subtraction, or if you have a constant rate of change, you'll see words like steady rate or slope. To be exponential, population growth, depreciated values, compounding interest, key words like doubling, tripling, halves, things that would represent quadratic form, free-falling motion of an object, area, revenue, Pythagorean theorem. So you can refer back to these as we go through the scenarios. Number 1, a hot air balloon has already risen 20 feet above the ground. At this point in time, it begins to rise at a steady rate of 2 feet per second. Part A, what type of function would best model the situation? We have a steady rate, so this would be linear. Write an equation that gives the balloon's altitude y in terms of the time x since it resumed its ascent. So slope-intercept form. Your rate, steady rate at 2 feet per second, and you began, the hot air balloon had already risen 20 feet above the ground. So y is equal to 2x plus 20. Second example. A population began with 100 people in the year 1990 and grew at a rate of 10% each year for the next 15 years. So we have population that's growing, exponential form. What type of function would best model the situation? Exponential. Write an equation that gives the population P in terms of the years T since 1990. So y is equal to a times 1 population growth is plus r raised to the t power. So we started with 100 people. The rate is 10%. 10% is your decimal, is 0.1 raised to the t power. The number of years since 1990, it says 15 years is what we're looking at. So if we reduce this just a little more, y is equal to 100. 1 plus 0.1 would be 1.1 raised to the 15th power. Third example. Marvin is making a blanket. He wants the length of the blanket to be 3 meters longer than the width. What type of situation or what type of function would best model the situation? So we're talking about area. Area is represented by quadratic. So quadratic. To give you an idea, we have a blanket, so just think about a blanket. He wants the length of the blanket to be 3 meters longer than the width. So the width and 3 meters longer than the width. Find an equation that would model the area of the blanket A in terms of the width W. So your area is equal to length times the width. Your length, W plus 3, times the width, W. Distribute, W squared plus 3W.